For example 3, we want to find the critical points of f of x equals x to the 3/5 times 4 minus x. We have a different kind of function here that's actually been factored, and we're going to figure out what its derivative is and figure out what its critical points are. Okay, so this is a rational exponent and a linear factor. All right, first step is to take the derivative again when you're finding critical points. So I'm going to use the fact that I can actually distribute this x to the 3/5 back in rather than having to do the product rule, which we could do f prime g minus ft prime. But I'm going to go ahead and distribute it back. X to the 3/5 times x is going to be x to the 8/5, as I have to find a common denominator before I can add these exponents. Here's my function. Now I'm going to take the derivative once I distributed that using the power rule. 3/5, pull it down and subtract 1 from the exponent, which will give me negative 2/5. Pull the 8/5 down, subtract 1 from the exponent, which will give me 3/5. So here's my derivative, 12/5 x to the negative 2/5 minus 8/5 x to the 3/5. Lots of fractions. Step 2, set the derivative equal to 0. So that's the first part of critical values, where the derivative equals 0. And I need to solve for x for that. Fortunately, I just have two terms. Make it a little bit easier. Now, here's what we're going to do in this particular case. We can see that both of these fractions have I can pull a 4/5 out. Okay, fifth is obvious. Up here, the LCM is 4, so I can pull 4 out. On top of the fact the smallest exponent is negative 2/5. Okay, so I'm going to pull that out, and I will be left with a x to the 5/5, or just an x, because if I multiply this back, I'd get 3/5. It's a little tricky there. If you're ever concerned about what you're left with in the parentheses when you pull something out, just divide it, and that will give you what's left over. Okay, so first of all, this will never equal 0 because it's a negative exponent. So we can roll that out, but we can set this equal to 0, and again, x to the 5/5 is just x. Let's take a look at what that looks like. It's going to be 3 minus 2x, because 5 over 5 is 1. Add 2x divided by 2, x equals 3/2. So here's our first critical value at x equals 1.5. But remember, critical values exist where the derivative doesn't exist, and we want to hone in on this term because it has a negative exponent. So when I put it on the bottom and make it positive, we can see that when x equals 0, the derivative will not exist. Okay? So, and that's true for any term that's x to the whatever, and it's on the bottom. And it's just a single term, it'll always be 0, because we plug 0 back in, you get 0 in the bottom of a fraction, and you cannot have that, it will not exist. So x equals 0 is also a critical value. So here's our two critical values, x equals 0, x equals 1.5. Remember, for step 5, we want to write out all the critical values. Step 6, you want to determine the critical points by plugging them back into the original. So I'm going to plug in 0 first. We see we're going to get 0 back, because 0 times anything is 0. So our first critical value, or point, is 0, 0. Second critical point, just plug into your calculator. That's extremely hard to do by hand. You're going to get 3.2 for your y value. So second critical point is 1.5, comma 3.2. Now here's where we really want to get at for this particular example. All right, we'll look at 1.5, 3.2 first. We can see why it's a critical value. It has a horizontal tangent. And when we plugged it back in, it ended up being a critical point. And it just so happens that the graph changes direction. Remember, that's not always the case for a critical value. Now, what I really want you to focus on is right here. Now, we have a vertical tangent here, and that makes sense. We know critical values are where the derivative doesn't exist or has a vertical tangent. And in fact, the derivative doesn't exist at a vertical tangent, right? Because it goes straight up and down. It's infinite. But here's the point. The critical points are not always extreme values. Okay? This graph doesn't go from increasing to decreasing or vice versa. It actually stays increasing, except for right here at the vertical tangent. So I want you to understand that, and I want you to see what critical points might look like. They might not always look the same, but they still have that twofold definition, where the derivative doesn't exist or where the tangent line equals 0. That's it for this particular example. you have any other questions about this or any other questions about critical points, let me know.